Hello students. In the last lecture, I discussed about ABC analysis, that is about always better control analysis. In today's lecture, I am going to discuss inventory models with deterministic demand. It is extremely difficult to formulate a single journal inventory model which takes into account all variations in real systems. In fact, even if such a model were developed, it may not be analytically solved. Thus, inventory models are usually developed for some specific situations. In today's lecture, I shall deal with the situations in which demand is assumed to be fixed and completely known. First of all, I am going to discuss the classification of inventory models. The models in which demand is assumed to be fixed and completely known. Such type of models are called economic lot size models or economic order quantity models. Now, economic order quantity models, I am going to further classify EOQ models. Three types of models are there in which shortages are not allowed. The first is demand rate uniform and the replenishment rate infinite. The second type of models are in which demand rate non-uniform, replenishment rate infinite. And the third type of models are in which demand rate uniform, replenishment rate finite. There are more three types of models in which shortages are allowed. The first type of models are demand rate, having demand rate uniform and replenishment rate infinite. Also, shortages are allowed. The second type of models are having demand rate uniform, replenishment rate infinite, shortages allowed, and the time interval is fixed. The third type of models are in which demand rate uniform, production rate finite, shortages are also allowed. Now we will discuss one by one model. First of all, we will discuss classical economic order quantity model in which demand rate is uniform and replenishment rate is infinite. This is one of the simplest inventory models. A stockist has ordered to supply goods to customers at a uniform rate, capital R per unit time, hence demand is fixed and known. No shortages are allowed. Consequently, the cost of shortage, says C2, is infinity. He places an order with the manufacturer every T time units where T is fixed and the ordering cost per order is, say, capital C3. Replenishment time is negligible. We can also call that replenishment rate is infinite, so that replenishment is instantaneous. That is, lead time is zero. The holding cost is assumed to be proportional to the amount of inventory as well as the time inventory is held. Thus, the cost of holding inventory I for the time capital T is C1, where C1 is cost of holding one unit in inventory for a unit of time. Capital I is cost of holding inventory I, and the capital T is time. The cost coefficients capital C1, capital C2, and capital C3 are assumed to be constant. Now, what is stochast problem? Now, the stochast problem is to determine how frequently he should place the order and how many units should be ordered in each order. Now, I am going to answer these questions. Say, if orders are placed at a interval t, if orders are placed at a interval t and the r is uniform rate, then quantity must be ordered in each order is given by capital R into T. Since the stock in small time dt is given by RT dt, the stock over the time period t will be calculated by this, that is integral from 0 to time t RT dt. Now R is constant, therefore we take it as outside the integral, this becomes t square by 2, 0 to t, which after calculation we will get half r t square. We will also write it as half rt into t. Rt is basically quantity, that is stock, half q into t. What is half q into t? That is area of inventory triangle OAP. I will also discuss this model with the help of this model diagrammatically. This is basically these are the time intervals. Small t are time intervals, and capital T is the total time. Q is the quantity placed at time intervals t. Then Q is given by capital R into T. After this, we will calculate the stock in time period T, as I earlier calculated that stock in time period T is equal to half capital R T square, which is further classified as half Q into T. This is equal to, this is O, and this is A, and this is P. Area of inventory triangle OAP is given by half base into height, that is q into t, which is like this: half rt square is equal to half qt. Now cost of holding inventory during the time t is given by the cost of holding the inventory during the time t is given by half. Cost of holding is capital C1, and the stock in time period is half RT square into C1. Therefore, cost of holding inventory during time T is given by half C1 RT square. This is half C1 RT square. Now, ordering cost to place an order is given by C3. Ordering cost for placing an order is given by C3. Therefore, total cost is cost of holding inventory during time t plus ordering cost to place an order. Total cost is given by cost of holding inventory during time t, which is given by this formula, that is half C1 RT square plus ordering cost to place an order, which is given by capital C3. Therefore, total cost during time t is half C1 RT square plus C3. This is the total cost. Now, average total cost, average total cost per unit time t is given by per unit time t is given by total cost divided by t, that is time. Total cost is half C1 RT square plus C3 divided by t. Thus, average total cost per unit time is half C1 RT plus C3 by T. This is average total cost per unit time T. Now, this average cost will be minimum. Say we represent this average cost, total cost per unit time as C of T. This C will be minimum if derivative of this is 0 and its second derivative is positive. This is basically first derivative test. We apply here derivative test to calculate the minimum value of average total cost. That is, its first derivative value is 0 and simultaneously its second derivative is positive. We apply these conditions, we get half C1R minus C3 by T square equal to 0. We take the derivative of this. We simply take the derivative of this. After calculating, we will get T is equal to 2C3 upon C1 into capital R. Also, add this d square Ct upon dt square, which is given by 2C3 upon t square, which is positive for every value of t, which is positive for value of t given above, for value of t given above. Thus the minimum for thus Ct is minimum for optimal time interval TO is given by square root 2 C3 upon C1 R. Also, optimum quantity to be ordered during each order is given by optimal quantity Q naught to be ordered during each order is given by capital R into T naught. Capital R into 2C3 upon C1R square root. After calculation, we will get it as 2C3 R upon C1, which is also known as optimal load size formula. Because this formula is due to R.H. Wilson, a mathematician, therefore it is also called Wilson's or square root formula. Also, this derivation I provided here, this we already discussed, that total cost during time t is half C1 RT square plus C3. Then average total cost per unit time is half C1 RT plus C3 by T. C will be minimum if first derivative is 0 and second derivative is positive. After calculation, we will get optimal time interval, which is given by this formula, and the optimum quantity Q naught, which is given by this. This is also known as optimal lot size because this formula is invented by R.H. Wilson. Therefore, it is also called Wilson's or square root formula. Further, any other quantity other than this will result in a higher cost. Now, the resultant minimum average cost per unit time is given by, I have already calculated average total cost per unit time, which is half C1 RT plus C3 by T. Now the minimum average cost per unit time is given by, put the value of T here. After putting the value of T, we will get this formula, that is square root of 2C1 C3 R. This is the minimum average cost per unit time. Also, the total minimum cost per unit time, including the cost of the item. If the cost of the item is also included, then the formula changes as square root 2 C1 C3 R plus cost of the item plus capital C into R, where capital C is the cost per unit of the item. If we change this formula above, that is formula for average total cost per unit time in terms of quantity, then this formula will be changed as half C1. Basically, quantity is equal to R into T. From here, we can calculate this formula, that is, this becomes half C1 RT plus C3 by T, which is further equal to half C1. RT is basically Q plus C3. We will calculate the value of T from here. The value of T, we will get it as value of T is T is equal to Q by R. This becomes C3 R by Q. Therefore, if we change the formula of average total cost per unit time in terms of quantity, then we will get this formula, that is half C1Q plus C3R upon Q. Also, average inventory is Q naught plus 0 by 2, that is Q naught by 2, and thus it is time independent. Now, it may be realized that some of the assumptions made are not satisfied in actual practice. For instance, it is seldom that a customer demand is known exactly, but replenishment time is negligible. Now, based on this, I am going to discuss one corollary. If in the above model, the ordering cost is replaced by C3 plus BQ instead of being fixed, then we have to prove that there is no change in the optimum order quantity due to the changed order cost. We can simply calculate it as the average cost per unit time is given by, I have earlier calculated this, that is average cost per unit time in terms of quantity is given by half C1Q plus C3R by Q. Now C3 is changed to C3 plus BQ, which is the new ordering cost. Replace this C3 with this C3 plus BQ. Then the average cost per unit time is half C1Q plus R by Q C3 plus BQ. Now again, for minimum cost, first derivative is 0 and the second derivative is positive. Apply these conditions on this, we will get Q node as square root 2 C3R upon C1. Now look at this optimal quantity. This is 2C3R upon C1, optimal quantity to be ordered during each order. And now look at this, that after the ordering cost is changed, again the optimal quantity is square root 2 C3R upon C1, which is same as above. Hence, there is no change in optimum order quantity as a result of change in the order cost. Now, there are some assumptions of economic order quantity models, and also there are some limitations of economic order quantity models. Let us discuss one by one. First, we will discuss about the assumptions in the EOQ formula, which the assumptions which we have made in economic order quantity formula. The following are the assumptions. The first assumption is demand is known and uniform. The second assumption is shortages are not permitted. As soon as the stock level becomes zero, it is instantaneously replenished. Replenishment of stock is instantaneous, or replenishment rate is infinite. The next assumption is that is lead time is zero. The moment the order is placed, the quantity order is received. The next assumption is inventory carrying cost and ordering cost per order remain constant over time. The former is linearly related to the quantity ordered and the later to the number of orders. The next is cost of the item remains constant over time. There are no price breaks or quantity discounts. The next is the item is purchased and replenished in loads or batches. The next is the inventory system pertains to a single item. This is the assumptions which we have made in our economic order quantity model. Now, there are some limitations to this model. What are that? In practice, the demand is neither known with certainty nor it is uniform. If the fluctuations are mild, the formula can be applicable, but for large fluctuations, it loses its validity. Dynamic economic order quantity models instead may have to be applied. The ordering cost is difficult to measure. Also, it may not be linearly related to the number of orders as assumed in the derivation of the model. The inventory carrying rate is still more difficult to measure and even to define precisely. It is difficult to predict the demand. Present demand may be quite different from the past history. Hardly any prediction is possible for a new product to be introduced in the market. The economic order quantity model assumes instantaneous replenishment of the entire quantity ordered. In practice, the total quantity may be supplied in parts. Economic order quantity model is not applicable in such a situation. Lead time may not be zero unless the supplier is next door and has sufficient stock of the item, which is rarely so. Price variations, quantity discounts, and shortages may further invalidate the use of the economic order quantity formula. Based on these limitations, we have further models with deterministic demand, which we will discuss one by one. Now we will clarify this classical economic order quantity model in which demand rate uniform, replenishment rate infinite, with the help of some examples. Let us discuss examples of this model. The first example is a stockist has to supply 12,000 units of a product per year to his customer. The demand is fixed and known, and the shortest cost is assumed to be infinite. The inventory holding cost is rupees 0.20 per unit per month, and the ordering cost per order is rupees 350. Determine the optimum lot size. Second, optimum scheduling period. Third, minimum total variable yearly cost. Now we have the following details, that is stock is has to supply 12,000 units of a product per year to his customer. That is, rate is given. Rate is basically 12,000 units of a product per year to his customer. If we convert this into per unit month, then we divide it with 12, we get 1,000 units per month. Further, the inventory holding cost is rupees 0.20 per unit per month. Inventory holding cost is represented by capital C1, which is 0.20 per unit per month. Further, the ordering cost per order is rupees 350. The ordering cost is represented by C3 in our model, which is rupees 350 per order. Now we have to determine the optimal lot size. I have already calculated the formula for optimal lot size. The optimal lot size is given by the formula square root 2C3R upon C1. That is, square root 2, C3 is 350, capital R is 1000 per unit per month, 1000 units per month upon C1, which is 0.20. After calculating, we will get 1870 units per order. Further, we have to calculate optimal scheduling period. Optimal scheduling period. Now, I already calculated the formula for the optimal scheduling period, which is given as T naught is equal to square root 2C3 upon C1R, which is further equals to 2. C3 is 350, C1 is 0.20, and the capital R is 1000. After calculation, we will get 1.87 months. Further, we have to calculate minimum total variable yearly cost. Minimum total variable yearly cost, which is also given by the formula square root 2 C1 C3R, which is further equals to 2 into C1, which is 0.20, into C3, which is 350, into capital R. Because we have to calculate yearly cost, we change capital R as, we take capital R as 12,000. After calculation, we will get it as 4490 per year. The next example is a a stockist has to supply 400 units of a product every Monday to his customers. He gets the product at rupees 50 per unit from the manufacturer. The cost of ordering and transportation from the manufacturer is rupees 75 per order. The cost of carrying inventory is 7.5% per year of the cost of the product. Find the economic lot size, the total optimal cost, the total weekly profit. Now we will go into details. We has rate as 400 units per week. Now the cost of ordering and transportation from the manufacturer is rupees 75 per order. That is ordering cost is capital C3 is rupees 75 per order. And the further the cost of carrying inventory is 7.5% per year of the cost of the product. That is C1 is 7.5% per year of the cost of the product per year of the cost of the product. Now he gets the product at rupees 50 per unit from the manufacturer. That is 7.5% of 7.5 by 100 into 50 rupees per unit per year. Further, we have to convert it into weeks. This we get 7.5 upon 100 into 50 by 52, as we have to convert it per unit per week. After calculation, we will get it as this 3.75 upon 52 per unit per week. Now we have to calculate economic lot size. We have the formula for economic lot size. This is basically capital R 400 units per week, ordering cost 75 rupees per order, then inventory cost of carrying inventory, that is rupees 3.75 upon 52 per unit per week. Now we have to calculate economic load size. The formula for economic load size is square root 2 C3 capital R upon C1. We have the values of all the coefficients, that is C3 R C1. Put the values here. After calculation, we will get it as 912 units per order. And the further we have to calculate the total optimal cost, including the capital cost. We have also to include the capital cost. Therefore, optimal cost is, because we have to order 400 units per week, and the product rate is rupees 50 per unit from the manufacturer. Therefore optimal cost is 400 into 50 plus square root 2 c1 c3 r. After putting the value of c1 c3 and r, and after calculations, we will get rupees 20,065 rupees per week. Also, we have to calculate totally weekly profit if the item is sold for rupees 55 per unit. Now, profit P is given as we have 400 items. Therefore, the price for 400 items is as selling price is 55 into 400 minus cost price is 20,065.80 rupees. After calculation, this is 22,000 minus 20,065.80 rupees. After calculation, we will get 1934.20 per week as profit. The next example is ABC Manufacturing Company purchases 9,000 parts of a machine for its annual requirement, ordering 1 month's uses at a time. Each part costs rupees 20. The ordering cost per order is rupees 15 and the carrying charges are 15% of the average inventory per year. You have been asked to suggest a more economical purchasing policy for the company. What advice would you offer and how much would it save the company per year? Now re- we have supply rate as 19,000 parts of a machine for its annual requirement, that is capital R is now 9,000 parts per year. The quantity is calculated by dividing by 12, that is 750 parts. Now the cost is rupees 20 part and the ordering cost per order is rupees 15 and the cost carrying inventory carrying charges are 15% of the average inventory per year, that is 15% of cost, that is 20 into 15 by 100, that is rupees 3 per part per year. The total annual variable cost is given by, we have also calculated this formula. The total annual variable cost is given by, this formula is given here. This is the formula, half C1Q plus C3R by Q. Half C1Q plus C3R by Q. We have value of Q as 750, C1 as 3, R as 9,000. Put all the values. After calculations, we will get annual variable cost as 1,305 rupees. The optimal quantity order is square root 2R C3 upon C1. After putting the values, we will get optimal quantity of order as 300 units. Also, the total annual variable cost is given by corresponding is given by square root 2 R C1 C3, R as 9,000, C1 as 3 rupees per part per year, C3 as 15 rupees. After calculation, we will get it as 900. Hence, if the company purchases 300 units each time and places 30 orders instead of placing 9,000 parts per year, the net saving to the company will be total annual variable cost, that is 1305 minus 900, that is 405 a year. Hence, if the company purchases 300 units each time and places 30 orders in the year, the net saving to the company will be rupees 405 a year. In the next lecture, I will discuss about the next classical economic order quantity model in which demand rate is demand rate is non-uniform, and the replenishment rate is infinite. Till then, thank you so much.